Okay. Should do. Yeah.
This meeting is being recorded. Yeah, good. Okay, so let's start. So the problem that I was trying to solve when I designed this was, well, curiosity, of course, but more specifically, it's often necessary to use some kind of binary serialization to send data as binary, some structures as binary data. The usual C-style approach, just use the C structure, cast it into const.char, send it, and hope the other one will have the same endianity and everything, and will correctly do the alignment. And in case he has a different platform, then well, pretty much you are stuck with the old way of doing that, because like now we have 64-bit systems and we have different alignment rules. So yeah, not quite a good approach. If we are working with some other programming language, such as Java, we could just take an annotation and it would generate as a function that would pretty much just go through every type and call some generate function on that, and we are done. But we are not quite able to do this in C++, because we need the reflection, which is supposed to be in C++26. And they are putting some effort into it, but it's like not guaranteed it will even be available then. So what do we do? Well, it turns out that it's actually doable already in C++14. Because, well, the committee actually standardizes things that sometimes allow doing plenty of unintended stuff. So although this is again a mistake, but in practice is actually a super useful mistake. So the question is like, how can we actually do that? So I wanted to write some code, so I need to see. Okay, so for start, let's say that we have some structure. I cannot, it wouldn't fit the line.
Scroll.
Okay.
That's not the reading price. Do you need the assembly part?
Later. Yeah, I assume that I can just make it much smaller now. I will need it by the end, but right now it's not necessary. Okay, is it good? Okay, so let's just declare some struct that we are trying to reflect, and inside we put like an integer, so a, something that starts with a, so it would be 8, and something that starts with c, so this one is clear. A float c starts with yeah, c, and starts with yeah, let's put there 5, because it starts with f like float. Okay, so okay, we got the structure and we are trying to reflect it. So actually, where do we start? Well, pretty much we have no idea. So let's just start trying to build some kind of framework around this. So for first, let's create some thing that can be converted into anything, so that we could aggregate initialize it using this kind of thing. So the font is too large. It just seems weird and distracting. So, okay, so forgot that I need the cheat sheet, so that I put the right name there, so that it matches the object inspector. So we have this object inspector, and we want to be able to convert it into anything. So we make a general conversion operator so that, wait, no, yeah, operator child. And so we need to return child is constructed, which means that pretty much anything we're trying to reflect will have to be default constructible. But if we are trying to cast stuff into binary, this isn't actually so much of a limitation. So now what we can do is that we can construct the test struct A is test struct. We can use empty brackets. We can do it with one argument. This template argument is not entirely necessary, but it will be useful later. Yeah, okay, I don't need to redeclare it. Okay, we do this again. And yeah, works with one argument. Can we do it with two arguments? Yeah. So let's try 3. We know that this will work because this is elementary school level. Still works. Let's try 4 arguments. And well, the surprise, it doesn't work. So we would like to create something that would react to this and realize that it's no longer working, and use this to actually verify that this is when there is enough and we can't go anymore. Can you actually move the laptop back so that I could use the cheat sheet, because it's just sometimes so specific that I still need to check it so that I keep the names of stuff. I mean, just put it here. But yeah, but they do. So
Let's make it more complicated.
So like, we need to make some kind of member counter. Designing some kind of something that could measure, that could like keep trying to construct it until it cannot. And in that case, we use finite to cause the overload to fail. So let's just start type name T, that's the type we are trying to reflect. Wait, no. Type name is name. And then this is enough for now. Yeah, so that's, yeah, we'll need some indexes. For now, well, let's make something that can count the members. So member counter, and this would be like the default overload that doesn't trigger in case we we are already trying too many members. If we try to construct from 4, we cannot try we cannot use its specialization. So that this is the one that we get when we are beyond the edge. So now we just construct per static size size, and this one will return so that the indexes is that we add 1 index with every iteration. The indexes were this was my mistake. Here is where here was an index supposed to be. or no, then we'll probably need, I will need both, so I'll just put the, also the index, although I don't need it. Yeah, this thing doesn't work anymore, so I'm going to erase it. I don't need it. So, okay, so let's make a specialization that would actually count the members. So now we don't got this FINA anymore, and we are trying to templatize it. So like, yes, we are moving the type again there. We have this indexes, but we are trying, but like, as I have suggested, we need this element names FINA. So let's just make sure that we can construct it. So we try to create a decal type of the attempt to construct it. So here we try to construct it, and we put there actually construct this object inspector P indexes and 3 points should work now. Yeah. Yeah, I don't need to declare this one because I'm just actually invoking it. Should be fine now. Okay, yeah, it's fine. So what this does is that it counts the members. Wait, actually I haven't done the size function. So now to count the members, we need to basically try to, basically we are just going deeper in this template and oops, okay, sorry, I blocked my screen. That's the make touch bar, not a good idea. So we are going to call recursively member counters gap or size from the previous depth. So again, let's try the same type. So T, no, it should be T asterisk because, well, maybe need it for spinite. And then we just do indexes and the size of indexes so that we add a new index there. And again, call get. This way we recursively go deeper, deeper, deeper until we count all of them. So now, if I didn't screw up, we should be able to count them. So member counter test struct, test asterisk. Yeah, that should be all.
Size there instead of get online 23.
23. Yeah, it's size.
Now for a second compilation passed and I was curious. But it wasn't used yet.
Yeah.
I really didn't understand. But this is a scary moment.
Yep, and we got the size. So yes, now we can learn the size. But well, this was the easy part. Here we actually at this place inside this operator child, we know what is the type. But this information is basically inaccessible because it was just using some spinai somewhere, and we are not getting any return values anywhere. If we construct something there, we will not get to the return value and we cannot pass it anywhere. So what do we do? So for now, let's digress. Well, should get the same thing now again. Yeah. So now I will just remove everything and let's just start some new, let's call it thought experiment. This seems actually completely unrelated. So, wait, how do I name it? Let's just create, for now, create the river, because we are trying to retrieve something. And we put there a function called int retrieve, which takes the retriever as an argument. We just forward declare it. This isn't much, but it's important that C++14 has added the argument dependent lookup, so that if we declare this as friend, if we call a function named retrieve without respect to namespaces and other stuff on anything that gets on the retriever type, then it will actually find us this function. This isn't glorious. So let's make template integer num struct saver, and inside we declare again a friend function that returns the number. This is argument dependent lookup. That means that if we actually do so out retrieve, and we just construct an instance, what does it do? Doesn't work. Undefined reference, because this function is forward declared. So what else can we do? We can create a saver. Oh, we don't even initialize it. And it returns 3. Because now we have a forward declared function called retrieve that is linked to the retriever type through ADL. And now we have formed and we have created an instance of the saver, and it has declared a function called retrieve that is linked to the retriever class with ADL. So now we can find it, this function. And this template has been instantiated to 3, so it returns 3. Okay, so what happens if I create another saver with 4? Conflict in declaration. Ah, yeah, because I gave it a C. Redefinition of retrieve, because now we have the template is trying to declare this function twice. Well, this kind of means that, well, C++ was supposed to be stateless. And I mean, the template evaluation is supposed to be stateless, so that that every template depends only on these arguments. This is actually not true, because if we just do this, well, actually by instantiating the saver, we have created the retrieve function, and previously didn't exist, now it exists. If we try to use a function that would use finae to test if it exists, we could find it if it exists or not. So What if we actually try to extend it? Template, integer, index. Now, yeah, retriever. Again, index, retriever, index. Now, what can we do? Well, not much, but yeah, now we need to specify which one we want to get. And yeah, we are constructing a table here. Of course, what other things we can do here is that we check which ones exist, find which one is the last, and once we know which one is the last, we can add one at the end of the list. The problem, so this way we can create a dynamic vector that is constructed at compile time. So this can be actually made even worse.
There is a question.
Yeah.
So like, is the friend function
the class member? Well, it's not a class member. It's a friend function that uses ADL to be linked to it.
So it's called hidden friends.
Hidden friend. Yeah, that makes sense. Okay, so I said we can create a dynamic vector that we just keep extending. We may mean that like the last value is the only one valid. We can like construct it to get some, for example, list of classes that we can construct for some self-registering factory or something like that. The disadvantage of this approach is that we assume that there is no state in template evaluation, so that if you repeat the same something with the same template argument, you will get the same result. So that you need to try or put always new template arguments there, so that you actually get create the search again, so that it just doesn't give you back the old value. So it's not so practical, but if you are, for example, adding classes into something, or if you use C++20, you just always put there an inline lambda, which is always a different instance. So you don't really have this problem. You just keep making it fresh every time. So you can just make a fresh search for the last element every time. But that is not quite what we want. What we would like to do actually is that we would like to get a generic lambda and call it on every element of the struct, right? This is probably the most general approach of doing this. Like we get just one function and it will give us a reflected struct, not reflected struct. Just iterate through the elements regardless of the type. Generic lambda, add it again, C++14, just put auto as the type of argument. You create an object that has a template operator that will just match whatever. So what we are trying to do here is that we are trying to save the information. So let's call it struct info getter. That's a better name, and this one will be struct info saver. All right. Yeah, we can just delete this because it won't compile. We just get struct info getter here. Okay, so we would like, so we need to know what is the parent struct. So type name parent. And again, we have index, and also we have the generic lambda, which we'll call visitor. Type main. Yeah, must be. Yeah, creating lions. Okay, visitor, parent index, visitor. Okay, Now we also have the same 3 arguments in this other thing. Okay, yeah, but we need to also copy these template arguments. Yep. Okay, so what we would like to do here is that we don't want just to get some random int we have saved. We actually want to call the call it on the specific member. So again, not doing retrieve, we're just doing void. But now the arguments. We have the visitor. Just put it const because it's more, it might be needed for const correctness. And we will actually need the offset of that. Yeah, this is it. Of course, the issue is that right now, as you are probably looking ahead a little bit, and you see that you cannot see the whole line, too many arguments. This is like the longest line that is needed in this code. No, this is the longest line that will be needed in this code anyway. So there is just this offset, okay?
Put it on your line.
It's not needed. Other lines will not be this long. So we are again not returning anything, but here we would like to save the type because we can type name child. Okay, so now we actually would like to get access to it. The offset is the argument we get, and we will be computing elsewhere. I will get to that. So for now, we are just calling the visitor on some with definition flat declare the number 6. Yeah, it's in line 12 now. So we are doing a reinterpret cast to the child type of, well, we first need to get actually our parents. So, right, cast. And once we get the address of the parent, which I forgot to put it there as a template argument. I knew there are a shitload of template or function arguments here. Yeah, this is the only case where we need this much stuff. Okay, here we are not casting it to parents, sorry. We are casting is to star. Yeah. And now we add the offset here. We cast it back to the child. And we got it. Yeah, no, we are calling the, well, we cannot use this now, but I have just let me switch to this prepared code. Okay, wrong window. Here is some test code that I had prepared for it, so that I don't have to write all the test code myself. This. So if I try to test it, I make a print me function that just prints everything. It's still called retrieve. Okay. I wanted to call it column member. Okay. Okay, so it's called column member, right? Is it compiling? What is the problem?
Very good question.
I assume that this older iteration had different code. What's the problem here? Reference star const main lambda. Yeah, the order of arguments is changed. how it was in on the original that I was trying to describe. Parent offset and visitor afterwards. Yeah,
Wow.
I put the order wrong. If we had 2 hours for this talk, I would just not copy paste this, but okay. Now, if you can see it, it actually did print these 3 elements using stat.cout. So we didn't know the types here while we were calling it, but it printed them correctly because it was able to learn the type. Because the type was saved here. So this is something that we will use later because we are going to make this because like as I have shown before, we will know this type here and we will be able to save it here in this object inspector. So now there is one more problem. We are investigating what type is it. And well, that's fine, but we also need this offset. So Miloš had previously a talk about something like a year ago, a talk about the layouts of Struct, that they have some standard layout and everything has its offset and its size. And there are some very specific rules that tell you how it is structured, so that everything has some minimal alignment and it's placed on the next position that isn't occupied yet and is aligned properly. So that we should be able to use this also to get actually get alignments. Again, we just use this thing that is a complete dummy. And the same thing for actually getting also the size. Okay. These are difficult to tell here, but here we can again determine them using the child type. So we just return a line of child. And here we do return size of child. Okay, so yeah, this should be const expert. I forgot about that part. Because, well, it would be useful if we are able to determine this at compile time to make our code faster. Other than that, it's not, I think it's actually not really necessary. But I have made a few changes, but we are not going to use them here. This is still just the example. So let's go. So let's just paste this into the original code. This object inspector. And previously we were declaring this struct info saver, right? So let's just create it here as well inside this child. Struct info saver. Yeah, we're just going to construct it and do nothing with it. I hope, well, I have disabled pretty much all the warnings, so I will not get the warning that I'm doing in wrong. So parent index, yeah, where did I get this int from? Yeah, that's the type. So it's child here. Now it's determined, except that we don't know the visitor here. So let's just add it as another template argument. We'll be having a lot of template arguments here, which makes the code rather ugly. I don't like it, but what can I do? So again, we are declaring visitor here. And now here we can do visitor. Okay, working? Okay. Again, here we need also the visitor. And we need it also here. And here. And here as well. We are just pushing it through because functional programming loves large numbers of arguments everywhere.
You don't need type name.
Yeah, I don't need because it's an argument. But I forgot to put the visitor here as well because I am actually trying to forward it to this object inspector so that I made the typo there. Yeah, is it now? It's still not compiling because here it is wrong. So I'm going to move my super duper visitor. So, okay, extract and deco type print. Okay, no, not okay. What's still the problem? Type int got visitor. Yeah, wrong order of arguments again. Okay, we still get that we have 3 arguments. So let's just try this code again that was originally meant for doing this kind of crap. So, okay, column member. And we now know, okay, what don't we know? We don't have an instance. All right, so we get an instance. And it should be fine now. Please. What's wrong? Column member. Oh shit, what is this? Is used but never defined. Is used but never defined. Why is it? Is used but never defined. Yeah, because it's forward declared, but why is it only forward declared? I was just actually calling this member counter. Why do I have to? Yeah.
I think the order is wrong.
No, that's not the problem. The actual problem is that this struct info saver that in this case everything depends on the order how things are being evaluated. The order of declaration doesn't really matter, but we absolutely need it to be evaluated as early as possible so that anytime we try to actually access something there, it is already we already have the return value. So what we can do here is that we need to make it actually dependence of this struct info saver. So we need to force it to be actually created. So we just create. We want this. So we are trying to access this. So if we try to access this value, we ensure that it is created. So we just require the here. We don't care if it is true or false. Actually, just getting this value does whatever we want. And now, because this conversion operator, we have no ability to actually fill the second template argument there. It has to be taken from the default value, and the default value ensures that we actually instantiate the struct, create these functions here, and that way they start existing, and we are able to get them through the struct info getter. And now we can print them. What is the problem? Of course, we actually want to iterate and actually finally get to the offset. There is a way of doing this, and we just create another utility function, template. So again, we will end up creating some kind of recursion that we just go recursively until we are out of elements. So we just call size the index, size the and offset, because we are going to know it here. We start at 0, so we know the first one, and then we'll need to calculate the next one with every iteration. In order to calculate the alignment, we need the previous one's alignment. It's just an algorithm basically, which is relatively simple. Statement T, statement. Yeah, we have a lot of template arguments here. We'll have to make it nicer in some helper function around it. So of course we cannot make this the final ones. We'll just call it for each member range, that we specify the range from which element until which element. The end will have to be filled by the helper function, and by filling this end, it will force to instantiate the size, so that before we are able to get to this for each member range, we will have to instantiate the member counter and the child and the struct info saver. So that for each member range can be just the function, just an object, and what was it called? Host visitor. Okay. It's a normal function for now. And also we are trying to call it in some way that actually looks relatively nice. So that we want it just to require the actual type that we are reflecting, and what we are calling on it. So this will be our holy grail for its member, and we are just taking again T as object, const visitor. Okay, and now here we just want to call the for each member range. So we are doing for each member range. Well, template arguments. We are starting at index 0, and is this thing. Did I declare this as const expr? Yes, I did. Okay, this one should be fine. This one was called only T, fortunately, so it won't be so long. Decal type visitor. Okay, wait, actually I don't need decal type because actually there is a template argument. So, and offset, we are starting at 0. Next line, this was also 0. No, this was 1 because this is most 1. The others will be determined from the arguments, and we are just doing again object. Is it true? Yeah. Okay. To make at this point, just to make sure we don't screw up, is actually pretty useful to do the static assert. No, we actually obtain this size elsewhere. We just do it const state int size will be this, and we want to make sure that size equals size of the struct to know that we have reflected it correctly. Otherwise, reflection failed. We did something wrong. We don't know what. So, okay, so now we put the size and we go into this for each member range. So, of course, we want to make a fixed number of iterations. So we just continue going deeper while index is smaller than n. And otherwise, we do some kind of finally. So I'm not going to go into the algorithmic detail of calculating the actual size, the actual offsets, because this is pretty much just find the lowest position that is divisible by offset, and yeah, that is a multiple of the alignment constraint, and it's just greater than size. And we have the max align, which is like from the previous iteration, and otherwise we can just access it. So I'll just copy paste this from the GitHub. So that I don't have to type this. Sorry for actually accelerating this a little. So yeah, we get alignment from the get alignment function. So then we calculate what will be the maximum align for the next element, and we just check if we need to make a correction here, and then we just get the alignment of this element that we are dealing with, and we call the visitor on it. Yeah, this won't do much because we just call it on the first element, which will be 0, and then we end. That's pointless. So we actually need to also continue to recursively calling the rest of the code. So yeah, so we calculate the next offset using this information we have now, and we use it as template arguments for the next calling for each member range, but we are starting from the next element. So again, we just rename it to visitor select again. Okay, so now it kind of should work if I didn't make a mistake. So I don't need all of this, and I should be able just to, no, actually do need this one. And I do for each struct member test, and then I use this template, this lambda as the next argument, and it should be all. Nope, was not doing. We didn't calculate the size correctly, apparently.
Because you are comparing number of bytes to number of.
Yeah, I'm comparing completely different integers, right? Yeah, because, wait, what was I actually supposed to compare? Aha, yeah, this was just that I have forgotten that this check was supposed to check something else. The point of this check is that if it is not constructible the way we would expect, and this is not supposed to be -1, because if member counter, if we are not able even to construct it from 0 arguments, that means that it's not default constructible, but every aggregate type is default constructible, which means that we are trying to reflect something that we cannot reflect. we can do this only on aggregate types. So that it just never, this overload never matches. We get this overload. We didn't put any indexes here because we didn't find any elements. So we get 0, -1. And in that case, it's all wrong and we failed. Yeah, so now what's the problem here? Get alignment was not declared in this.
It's actually doing something else.
Wait, what?
In the error,
You mean,
big scroll the arrow to the.
yeah, what was there?
Yeah, it's aligned. No, go back.
Oh,
You mean alignment.
get alignment. How did I call this one here? Get align. It's called get alignment, get size. No. Start info getter. Get alignment.
The name get alignment before the G, I think. Yeah, it's typo
Where?
on the definition. Get alignment.
Aha. Yes, I forgot the N. And here it is also forgotten.
No, it's not.
Yeah, still this slow.
Aha, yeah.
So the error message is again.
Yeah. Yep. Now we have iterated through all these elements. And of course, there are several other ways that we would really like this to fail in case something is wrong there. So I had another check in the code that I put here, that if we get to the last element, we can actually still continue calculating the size, which has the advantage that at the end we should get the same value as we would get from size of. And if we get this, if we calculate the size and it is the same value as we get from size of, which is always correct, it means that we screwed up again. So this is another validation. Another validation that we can put it there is this check that it is actually an aggregate. Because of course it will not work in non-aggregates. And that's it. So this way I have
Elegant.
it's actually it's in the end it's 80 lines of code. Just copy paste it somewhere and you can reflect your structs and create a binary serializer just by making an overload for all of your types. In pure storage where I'm working, I've created this, and then we have used a bunch of regexes to change the declaration into C++ structs, and we have implemented the NFS protocol with that. And yeah, basically, as long as the types were, it's like you didn't make anything really crazy, it just works. I really avoided, like, I didn't get any undefined behavior from this, even while developing this code, actually, simply because I put there these checks and it just either fails to compile or works. And yeah, it's not long. You can, so it's like really portable, easy to place anywhere and so on, and it just does the stuff. Okay, so we can go to questions.
Have you tried using index sequence to simplify the paragraph? Because this feels like it's a good candidate for use.
Index sequence is useful.
I'm not sure if it's C++ 14. Is that a requirement? Because I don't know if index sequence is 17 or 14.
Well, I use if context pro, which is C++ 17, but I would have to use some function overloading if I wanted to make it work on C++14, but it's not something that's not
But that
doable.
wasn't the hard requirement.
Yeah, I didn't take it as a hard requirement. I took it just doing stuff that like it could be doable in C++14 if I altered the code slightly, but it would just, if I did it with overloading, it would be impractical.
So have you looked at index sequence? As
I have been using it, but I actually need to build this index sequence in my own code because I'm using the indexes as arguments to the where is this object inspector that is used here. And I need this template, this argument pack to grow with every iteration actually, because I need pretty much in the object inspector, even if I wasn't doing further construction using the struct info saver, I would still need this index just for the purpose to unwrap the argument pack into a bunch of individual arguments to construct this struct.
You should leave your email or something like that. So once this settles and the shock factor goes away, we can actually rest. So this is the second time I'm listening to this. He did it once, like in the company, and I'm still like there is just a point at which the brain starts compiling this.
To be honest, I did not invent this trick. I have seen, I did come to some crucial points myself, but I didn't figure out all the trickery. I found it in some project that like I was searching for something else and I ended up finding this. I spent like several hours studying what the code meant from this guy. There was actually a lecture on YouTube where he was explaining it, but unfortunately this talk was in Russian. So I had to just stare at it and experiment with it until I figured out what he actually meant by that. His project wasn't taking a different approach. He was trying to construct a tuple which had the same memory layout as the object, and he did a reinterpret cast from the object to the tuple, and then he could iterate through the tuple. So I changed it at that point. But yeah.
Do you have any limitations on the compiler side on the number of types or prolong as compile times?
It didn't seem to, well, it probably isn't as fast as you just wrote it by hand, but I wasn't noticing some particular delays. Other than that, the code I wrote works on GCC and client, but not on MSVC. I know this trick works on MSVC too, but because I don't have access to MSVC and just trying it on Godbolt wasn't quite complete. So I didn't figure out how to get it working on MSVC. But if I just do the basic thing with using the ADL to create stateful metaprogramming, this part worked. But something with its templates didn't quite work there. I'm not sure. I think it might be, well, first thing what I was noticing with MSVC is that it had slightly different order of evaluating things. So some implicit dependency might still remain there, that something is evaluated too late and just saves the struct info saver with two little elements. That might have been one cause. Another problem might have been that it actually allows a few extra stuff that shouldn't be allowed by standard, and Sphina sometimes passes when it shouldn't. this, like, it's one of these, but I didn't investigate it deeply.
Did you try to finish it minus?
Uh,
Because
no, I forgot about that.
it changes completely the two-phase evaluation of templates.
Yeah, I was
Default is the recursive compiler there.
yeah, back in the time when I was working mainly on Windows with MSVC, I was using this quite often. Exactly, was solving these problems, but right now I don't have Visual Studio anywhere, so there is something that prevents it from working. Other questions? Any steps that you would like to explain? Oh, you're just scratching your head.
Okay.
Yeah.
Online, when the edit file is needed for the template, okay,
Yeah, well, actually, it wasn't working until I put it there. The problem is that I need to enforce that instantiating that simply evaluating this template argument, whether this finite passes or not, will require checking if this operator passes and actually creating the struct info saver, which means that the struct info saver will be constructed just by evaluating if this template, if this overload matches or not. And that is even before this part of the code triggers. Because, well, I just need to create the struct info saver somewhere. I have shown you that, well, if I just put it into main, I can just make it a global variable. Or in practice, I can just create a function that does something absolutely unrelated. I declare the struct info saver and it does its job. However, in here, I need to ensure the templates are evaluated in a specific order. So I'm adding artificial dependencies between things. And I need a struct info saver just for that purpose. Maybe I will need to add some additional explicit dependencies to get it working on MSVC2. I think that would be probably the cause, because I know that GCC and Clang are quite close when it comes to the evaluation of things, but Visual Studio is quite different. And this order shouldn't matter unless you are using this, because if you are doing stateful metaprogramming, that means that things that shouldn't be in order, where the order shouldn't matter because they should be unrelated, now they are related. So we need to add explicit dependencies on things, even if apparently we don't really need them. Okay. Maybe I'll just write the GitHub link somewhere.
Are there any questions online? I see some.
There are 8 questions, but
No, we answered all of them as we went along.
Okay.
yeah, I will put the link on I will put the link on the Discord.
Yeah, and I'll also put it on Meetup.
Yeah. Or you have it open in your browser right now. So.
Yeah, I guess that's it then.